Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to have an application of definite integration. We're going to find the volume of a solid. And in this case, the solid is going to be generated by revolving the region bounded by two curves. One is a quadratic and the other one is a line. And we're going to revolve the region bounded by these graphs of the equations about the x-axis in the first case, and also about the line, horizontal line, y equals 1. Let me just show you what kind of like three-dimensional object we are talking about by revolving a region around x-axis or y equals 1 horizontal line. All right, here is the region mentioned in the problem. You're going to see the details of this in the video. So in the top, you have the quadratic, in the bottom, you have the linear. And I want to revolve this region about, let's say, first x-axis, okay? So as you see that, after the revolution, you get this three-dimensional picture, as you see. And in the second case, I want to revolve the same region about y equals 1. And here we go. We have the same region bounded at the top by the quadratic and at the bottom by the line. So if you revolve this around, this is slightly different from what we got in the earlier case. We have like as you see inside, there's a cone-shaped three-dimensional object. It's taken out of the full volume. In the other case, that was slightly different from that. Yep, this is what I'm talking about. So as you see, like there's a bigger hole inside the three-dimensional object. Okay. So at this moment, I want to remind you what technique we have at hand, and either like disc or washer, and how this technique is applied, but in a very brief way, and we're going to hit the road. So here is the table that represents the volume of a solid of revolution by the disk method, and we have two different formulas popping here. One is the horizontal axis of revolution, the other one is the vertical axis of revolution. I can tell you right off that in this question, we're going to look at the horizontal axis of revolution because both the x-axis and the y equals 1 line are horizontal. So we're looking at having a slice in the region, that yellow slice in the very left corner over there. Okay, so we're going to have a slice horizontal to the axis, vertical to the axis of revolution. Okay, so once you revolve that little slice around the axis of revolution, this is the disk that you get at the end. Okay, and this is the disk method, and we're writing down the volume of the representative disk first and integrate it through all axes within the region. And here axes are bounded by A and B, A on the left, B on the right. So going back to the formulation here, we have pi times capital R squared is corresponding to the area of the disk, and multiplying that by the thickness dx, that gives us the volume of the representative disk, and integrating that from A to B is the whole volume. Okay, so let's also look at the washer technique real quick. So in the washer technique, the slice has a distance to the axis of the revolution. So that's why when you revolve that slice around, you're going to get a punctured disc or a washer. Okay, so for that reason, you should know what the inner and outer radii are before you write down the volume. In fact, let me just make this picture a little bit bigger. As you see, once you revolve it around, you get a washer, and pi times capital R squared times dx is going to be the volume of the outer washer, which is the full washer, no puncturing, right? And if you look at the pi times little r squared times dx, that's the volume of the punctured part. So the difference of those volumes would provide us exactly what the volume of the washer is. So pi times capital R squared minus little r squared integrated from A to B dx. That's the volume obtained by revolving this region around. Okay, so this was a long intro already, so I want to just stop right here, and why don't we go ahead and start solving this problem. All right, so we're given two equations, And apparently, the graphs of these two equations bound the region mentioned in the problem. And what we're going to do is we're going to revolve that region about the x-axis in the first part of the exercise. And the second part, we're going to revolve the region about the line y equals 1. But to be able to construct the region and to be able to graph it accurately, we need to find the intersection points. Okay, and to find that, to find them, so we have to set them equal and solve for x. Okay, let's see. Why don't we add x minus 4 to both sides of this equation so that the right-hand side becomes 0 and the left-hand side is minus x squared plus 3x, and pulling out negative x on the left-hand side, in fact, tells us what the solutions are. One is x equals 0, and the other one is x equals 3. So these two curves intersect each other at two different instances. One is when x equals 0, and the other one is when x equals 3. Okay, so please go ahead and use your graphing calculator to plot these two equations for x min to be 0, x max to be 3. And let's see what we get. All right, so this is how the region looks like. At the top, we have the blue curve, that's the quadratic f of x. And in the bottom, you have the purple curve, that is the linear function, right? And the region mentioned in this problem is the green region, stuck in between blue and purple curves. And what we're going to do is to revolve this region about x-axis, okay? So I can sort of technically show how the three-dimensional object looks like after the revolution. So essentially, I'm going to give you the original three-dimensional shape in a few seconds, but let's just hypothetically revolve this region about x-axis, and then this is so like how the three-dimensional object would look like. Okay, and you also have the outer part, right? That also rotates. Okay, let me just show you like a better picture here. So this is the region you start with. Okay, and you keep revolving this region around x-axis. Okay. And as you revolve that, this is the three-dimensional object you get. And in the middle, you see like a cone-like shape, and then that's taken out. So inside of this part, so as you see like this part, which is the inside part, right, going all the way like a cone. So that part is empty. Okay. So, all right. So in the washer, we're going to apply the washer method, by the way, to be able to find the volume of this three-dimensional object. And to be able to apply the washer method, we're going to take slices vertical to the axis of the revolution, okay? So I put like two representative slices from the region, and you can choose different slices if you want to. Let's say like this one comes with thickness dx, and this one comes with thickness dx. Here, one observation is that when you revolve this around, okay, so let's just revolve hypothetically one slice. You see that you get a punctured disc or a washer with thickness. So this comes obviously with thickness dx. Okay. And the volume of this washer here is determined by the inner radius here, as well the outer radius. I'm going to call the inner one little r, outer one is capital R, okay? And inner R and capital R are totally determined by exactly where this slice is taken. So for that reason, what I'm going to do here is that I'm going to say that this slice is x units far from the origin, which is in fact the left end of the region, okay? Let's say it's x units far from that, and little r is determined by the purple curve, right? Because that's the height from the x-axis to the bottom portion of the slice, and that's 4 minus x. And if you change x, if you change different, if you get a different slice, so that r is going to change obviously depending on that. Okay, like here for example, r is going to be smaller than this r because the way the curve is defined, the line is defined. Okay, and the capital R is determined by the blue curve, and that's in fact 4 plus 2x minus x squared. Okay. And if you want to find the volume of the washer here, so what you do is you multiply, you look at pi times capital R squared. That's the area of the surface of the washer, and if you multiply it by dx, that's the volume, the height of the washer, right? And you're going to also subtract pi little r squared dx, and this is the inner part of the inner disk, in fact. So we puncture that, we take it out, right? So that's why I subtracted the volume of that. Okay, so this is going to be our formula to use. So for that reason, I am going to place those in my integration formula, and let's see what we're going to get. So outer volume of the outer disk minus the volume of the inner disk. That's what we're going to do. Okay, there we go. So let's go to part 1, in fact. Okay, part 1. So the volume is pi times capital R squared, which is 4 plus 2x minus x squared, and 4 minus x squared is little r squared times dx. And this is the volume of only one washer. So to find like the volume of the whole three-dimensional object I showed you in the picture, we need to change x from 0 to 3. Okay? And from this moment on, it's all about the definite integral calculation. Okay, so you have to expand everything out and use the power rule for integration. So I do not want to go to details of that, but I'm going to tell you what I got from my end. If I simplify the difference of two polynomial terms here, so let me just write it down right away. You can just like pause the video and work through that by yourself. Okay. And this is kind of nice because you can use the power rule for integration now and towards using fundamental theorem of calculus. Okay, x to the 4th divided by 4 plus minus 5x cubed over 3 plus 24 x squared over 2, and the lower limit is 0, upper limit is 3. Okay. Please find the exact value rather than the calculator value. And what you're going to do is just plug in 3 first, and plug in 3. So pi times 3 to the 5th divided by 5, 3 times 3 to the 4th divided by 4, 5 times 3 cubed over 3, plus 24, 3 squared over 2. And then minus, subtract 0 all the way. But if you subtract 0, as you see, all x terms are gone. So it's going to be a complete 0 here. Okay. And if you simplify this expression here, and if you keep the exact value, so I'm going to write what I got in my end. Okay. So 153 pi divided by 5. Okay. Right, this is what we get for the volume of this three-dimensional object, okay? And inside of that, this part is sort of like completely empty, okay? So the volume is 153 pi divided by 5, okay? All right, so we use the washer method again, and in the washer method, we revolve the slice around the x-axis, but you get a punctured disk after the revolution. So what you need to do is just to calculate the outer disk, the volume of the outer disk, and the volume of the inner disk, and subtract. Okay. All right, so I'm going to continue part B in the next video. Please move on to my next video to see what I'm going to do for part